So, good day. Today we are going to be solving about parallel pipe systems and reservoir problems. But before we discuss how to analyze pipes in parallel, it is important to briefly mention how to analyze pipes laid in series. So here, the water is flowing from first tank to second tank through the pipes which is connected in series. Now, if we observe the system, the rate of flow or discharge Q from here will remain constant as the water flows through the pipes. And to get the total head loss from A to B, it is just going to be the summation of all the major and minor losses combined. So, as fluid goes into the pipe here at pipe 1, there is loss. So, that is our HI as the fluid goes in. And plus the frictional loss in pipe 1, which is HF1, plus here we have a minor head loss due to sudden contraction, or HC, plus again frictional head loss in pipe 2, and again um, a minor head loss due to sudden enlargement, which is HE, plus the frictional head loss in our pipe 3, and lastly our HO, which is also a minor head loss as fluid goes out of the pipe. Now, and thus we have this principle in pipe series. But here, the pipes in parallel, we can see that the principle has changed. As the flow goes in, here, Q, it will be distributed to pipes 1, 2, and 3. So, of course, it will pass through all three pipes unless it's closed or it has a barrier. So in this figure, we can say that the total discharge, Q, must be equal to the sum of the discharge of pipes 1, 2, and 3, which is called our conservation of mass. And now the conservation of energy, we can express this as HL1 or head loss 1 is equal to head loss of 2 and the head loss of 3. So in other words, the amount of energy lost in pipe 1, regardless of its diameter, roughness, or length, is going to be the same as the head loss in pipes 2 and 3. So, in summary, we can say that a parallel pipe system is a configuration where multiple pipes are connected in parallel to each other, meaning they share the same inlet and outlet points. And this setup allows fluid to be divided among the pipes, distributing the flow rate and pressure evenly across the system. Right here we have our head losses formula. First, we have the Darcy-Weisbach equation, which is HL is equal to FLV squared over D squared G, or HL is equal to 0.0826 FLQ squared over D to the power of 5 for circular pipes in SI unit. And F is equal, or I mean F is our friction factor for the Darcy-Weisbach. And for the second one, we have Manning's formula. HL is equal to 10.29 N squared LQ squared over D to the power of 16 over 3. Or we can go with HL is equal to 6.35 N squared LV squared over D to the power of 4 over 3, where N is our roughness coefficient. And as for Hazen-Williams, we have head loss is equal to 10.67 LQ to the power of 1.85 over C to the power of 1.85 times D to the power of 4.87, where C1 or C is our Hazen-Williams coefficient. And now let's start our first problem. The total flow in the pipe system in the figure is 0.86 meter cube per second. Assume F is equal to 0.032 for all pipes. Find the flow rate in meter cube per second in pipes 1, 2, and 3. So the problem stated that our Q is equal to 0.86 meter cube per second. And now, as Q goes in,
or the fluid goes in through the pipes, it is going to be distributed in pipes 1, 2, and 3. We have our Q1, Q2, and Q3. And that is what we're going to solve for. Using our Darcy-Weisbach equation, we have HL is equal to 0.0826 FLQ squared over D to the power of 5. We can get our Q. We just need to isolate it from the equation and get our unknowns. So isolating it from the equation, we've got Q is equal to the square root of HL times D to the power of 5 over 0.0826 F times L. And our HL is unknown, but we have our given QT is equal to 0.86 meter cube per second. Remember, right? And note that QT is equal to Q1 plus Q2 plus Q3. And our HL1 is equal to HL2 is equal to HL3. We're going to be combining these equations to get our answers, the flow rate of pipes 1, 2, and 3. Now we solve for our Q's 1, 2, and 3. And starting off with Q1, we've got our equation, our formula earlier, which is the square root of HL times D to the power of 5 over 0.0826 F times L. Well, this is good, but we can make it something easier by getting this answer of D to the power of 5 over 0.0826 F times L, representing it as K, so that the square root of HL will be left, and so we got an equation of Q is equal to K times the square root of HL, so that if we put it into the calculator, it won't be lengthy and it will be easier to solve for the unknown HL. Now, for K1, we've got a diameter of 400 millimeters, so 0.4 to the power of 5 over 0.0826 times 0.032 times 400, and the square root of that is equal to 0.0984. That is our answer for K1. Well, take note that this isn't finding the value for Q, but the value for K. And we can use this equation in finding for Q's pipes 2 and 3 as well. Now, for K2, we've got a diameter of 600 millimeters, so 0.6 to the power of 5 over 0.0826 times 0.032 times 350, and the square root of that, and the answer to that is 0.02899. And lastly, for K3, we've got a diameter of 500 millimeters, so the square root of 0.5 to the power of 5 over 0.0826 times 0.032 times 420. So this is just simple substitution, and we've got an answer of 0.1678. And now that we've got the values of K, we can now input it to this equation, and so we've got it here in solving for our Q. Now we have our Q's 1, 2, and 3. So for Q1, we have 0.0984 times the square root of HL, and for Q2, we've got 0.02899 times the square root of HL, and for Q3, we've got 0.1678 to the square root of times the square root of HL. So that's our value, yet we've got to find our HL. And we recall that QT is equal to Q1 plus Q2 plus Q3. And our QT, we have it in our given, stated in a problem, 0.86 meter cube per second here. And so we put it in the equation, 0.86 QT, our total flow rate. So Q1, this, Q2, and Q3, the summation of that, we put it into the calculator using shift solve technique, and we got HL, or the head loss, of 2.392 meters. And now that we've got our head loss, we can now multiply this by the values of K in order to find the values for Q's 1, 2, and 3. And that is what we're aiming to find. That is what the problem asked. And now this is the answer. Q1 is equal to 0.152 meter cube per second. For Q2, we have 0.448 meter cube per second. And for Q3, we have 0.259 meter cube per second. And if we sum it all up, it's going to be, we have an answer of 0.859, which is, if we round it off, we got 0.86. And recall from our previous, the QT, it is also 0.86. So 0.86 is equal to 0.86. So that means our answer is correct. So let's move on to problem number 2. In the figure shown below, it is desired to pump 0.03948 meter cube per second of water from stream to a pool. Calculate the total pumping head in meters. So using the energy equation, we can find the total pumping head, which is the head added of the pump. So in this figure, we got a given Q1, which is equal to 0.03948 meter cube per second, right? It is stated in the problem. We've got no Q's 2 and 3, but we know that Q1 is equal to Q2 plus Q3, because what goes in and out of this pump is equal. It's just equal. And also, we have HF1 over here, frictional loss in pipe 1, and frictional loss in pipe 2, and frictional loss in pipe 3. But the frictional loss in pipes 2 and 3 is just the same, right? So HF2 is equal to HF3, since this is parallel. And so we can say that the head loss from A to B is going to be equal to HF1 plus HF2 or HF3. It doesn't matter. And using these equations, this is equation 1. This is equation 1. This is equation 2. And this is equation 3. We can find our head added. And going back to the problem, we are given a Hazen-Williams coefficient. So we're going to use the formula for Hazen-Williams, which is HL is equal to 10.67 LQ to the power of 1.85 over C sub 1 raised to the power of 1.87 times D to the power of 4.87 in finding our head loss. Now let's try to solve our problem. From equation 3, HF2 is equal to HF3, we are going to simply substitute the given values of pipes 2 and 3 into the equation. So 10.67 times the length, which is 1525, times Q2, which is unknown, raised to the power of 1.85 over 110, the Hazen-Williams coefficient, raised to the power of 1.85 times 0.2 raised to the power of 4.87 is equal to 10.67 times 915 for pipe 3 times 900 times the Q3, raised to the power of 185, it is also unknown, over 140 raised to the power of 185 times 0.15, the diameter. We simply convert it into meters, and raised to the power of 4.87, and we can get the value of Q3 in terms of Q2. So we transpose Q3 to the left side in order to arrive in an answer of 0.787 Q sub 2. And now from equation 2, we have Q1 is equal to Q2 plus Q3. So this is all already given in the problem, right? This one. So 0.03948 is equal to Q2 plus 0.787 Q sub 2, what we got earlier. And we have an answer of Q2 is equal to 0.0221 meter cube per second. And now from equation 1, we can get the head loss. So head loss of from A to B, or the total head loss, is going to be equal to the head loss of pipe 1 and pipe 2. So 10.67, again substitution, we can get the answer 26.801 meters. Now that we got our head loss, we can now proceed to the energy equation between A and B. So EA is equal to EB. EA minus the head loss of AB plus head added is equal to EB. Now, we got no pressure head and velocity head, so we can say that it is 0. But we have an elevation head of 47 meters over here and 90 meters for B. So input it, ZA 47. The answer we got earlier, 26.801 minus, because it is head loss, and the head added, what we are looking for, is equal to 0, again, cancel, plus 90 for the B, the elevation for the B. So we got an answer of 69.8 meters. And so the total pumping head in meters is 69.8 in this problem. Problem number 3. For the pipe system shown in the figure, N is equal to 0.013 for all pipes, and the flow in pipe 4 is 12 cubic feet per second. Determine the head loss in pipe 1 in feet. So, we are going to find this head loss. And notice that as Q1, as fluid goes in there, it is going to be distributed in pipes or sections 2 and 3, and going out in section 4. So recall that Q in is equal to Q out. So we can say that Q1 is equal to Q4. And we have a given that Q4 is equal to 12 cubic feet per second. So it is going to be like that. So we are already familiar with this equation, right? The discharge Q is equal to A times velocity. So we can use the Manning's formula in finding the velocity. Since we are given the Manning coefficient N, we can find it, and the formula is 1.49 over N times the hydraulic radius raised to 2/3 times the slope raised to 1/2. And slope is the rise over run, which is the ratio of the head loss over length. And now we arrive into this formula. We just input the V in Manning's in here. And to expound, we've got area, pi over 4d squared, copy, 1.49 over N, times R, which is the hydraulic radius. The formula to that is area over perimeter, and perimeter is the pi times the diameter, having d over 4 is to 2/3, and S, copy. And thus simplifying the equation, we can get a head loss of 4.37 n squared LQ squared over D 6 raised to 16 over 3. That is going to be our equation in feet. Now let's try solving the problem. What is asked is we need to find the head loss in pipe 1. So we're going to use the Manning's equation we've got earlier, which is 4.637 n to the power of 2 times L times Q to the power of 2 over D to the power of 16 over 3 in feet. So the head loss for pipe 1 is just a direct substitution, this one. So 4.637 times the N, which is 0.013, and 1,500 times 12 for our Q, and 24 over 12 to make it meters, to the power of 16 over 3, and thus we got a head loss of 4.20 feet. And that's it for our third problem.
Moving on to our next topic, we have pipe connecting reservoir. So, what is a reservoir? So, it is a large storage of water. And in these problems, we should still consider head losses since reservoir has a connection to the pipeline system. And moving on,
The first three reservoir problems in the figure shown determine the flow rate into or out of each reservoir. Use F is equal to 0.02 for all pipes. So here in the figure, we have reservoirs A, B, and C at elevations 190 and 70 feet respectively. So at first, we don't have any idea about pipe 2 or reservoir B, whether it will receive water or it will give off water. So we can have a trial and error, but it's a waste of time. So, the best suggestion, according to most sources, we should assume that there is no flow at pipe 2, or simply Q2 is equal to 0. Let's just assume. So, if Q2 is equal to 0, then HL is also equal to 0. So, therefore, in RHGL, since we have no head loss, it is just level. So, at junction P, we go up and level at reservoir B. And we have a note that HGL slopes downward in the direction of the flow. So from reservoir A, it is going to flow from left to right, downward. And in reservoir C is downward from right to left. And given the elevations, we can find our head loss. So here is HF1. That is going to be 100 minus 90, which is 10. Here, HF3, because HF2 is 0. This is going to be 90 minus 70, which is 20. Now that we have our head losses 1 and 3, we can now compute for our Q1 and Q3. Using the Darcy Weisbach formula in English unit, we have HL is equal to 0.0252 FLQ squared over D to the power of 5. We're just going to substitute the values of our pipe 1 and our head loss of 10 feet here in the formula. So we've got 0.0252 times 0.02, the F here, and times 1200, the length, times the unknown Q here, over the diameter of 24 over 12 to make it meters to the power of 5. And we arrive into an answer of 23 cubic feet per second. Same goes for our H3. We can get Q3 is equal to 17.359 cubic feet per second. And since Q1 is greater than Q3, that means that B will receive water because Q1 is greater than Q3. So it is assumed that some of the discharge will go to B. Going back to our figures, since B will receive water, we're going to replot the HGL of reservoir B that is going to slope downward from left to right. So, okay. So, the flow is here and it goes here and downward. So that is going to be the direction of our flow. And the head losses will, the values of it will change as well. So let's just erase it for a moment. So we still have here our H1, HF1, this is our HF3, and our HF2. HF2. So let's try solving it again. From here to here, we got 100 minus 70, and our H1 and H2 is going to be equal to 10, since 100 minus 90 is equal to 10. So that means HF1 plus HF2 is equal to 10. While HF1 plus HF3 is equal to 30, right? 100 minus 70 is equal to 30. Now we have here the following equations that are needed in order for us to find the Q. So Q1 is equal to Q2 plus Q3, H1 plus H2 is equal to 10, H1 plus H3 is equal to 30. So in solving for the frictional loss using the Darcy Weisbach, we already got our H1 earlier, right? This one. And H3, this one. So let's just solve for H2. So 0.0252, substituting all the values for pipe 2, diameter of 12, and a length of 500. So here, 500, 12 over 12 is equal to 1. So we got H2 is equal to 0.252 Q sub 2 raised to the power of 2. Now this process is already familiar because I already used this approach earlier for our parallel pipe system. So we let H1 is equal to X. So it's going to be Q1 is equal to 7.274 times the square root of X. So it is just going to be like this one. So X is equal to 0.0189 Q1 squared. So we take this constant, divide that in order to get our Q 189. So we're left with X over 0.0189, and in order to cancel the squared, we need to square root. So our Q1 is going to be like 1 over 0.0189 times square root of X. So the answer to this is this one. And as for H2, it says here that H1 plus H2 is equal to 10. So we have our H1 is equal to X already. So that means that it is going to be 10 minus X. As for H3, it is going to be 30 minus X. So these are the following values. And we still don't have the value of X. So we need to substitute it to the first equation. Q1 is equal to Q2 plus Q3, and shift solve technique, we got 8.187 feet. So solving for our Q's, Q1, Q2, and Q3, we have 20.813 cubic feet per second, 2.682 cubic feet per second, and 18.131 cubic feet per second, respectively. And that's our answers to the problem number 1. So for second problem, in the pipe system below, use Manning's formula given n is equal to 0.011. Compute the discharge flowing towards reservoir C. So in this figure, we have here reservoirs A, B, and C connected at junction P, having elevations of 30, 24, and 15 respectively. At reservoir A, we have a length of 1,200 meters, 300 millimeter in diameter. And for reservoir B, we have 1,400 meters having 200 millimeter diameter. And for reservoir C, we have 1,500 meters and having 150 millimeter in diameter. And in this case, we are given a datum that the datum is inclined, I mean, the datum is lined here at reservoir B. And our note, we note that HGL slopes downward in the direction of the flow. So the hydraulic grade line here at A is going to slope downward from left to right. And as well for C. And what is asked in the problem is that we compute the discharge flowing towards reservoir C. But in order to do that, we must first find the head losses of A and C. And we can get that by um, getting the difference of the elevations A and B and C. So here we have H1, and we have here H2. So H1 is simply just the elevation of A minus the elevation of B, 30 minus 24. H1 is equal to 6. H3, this is H3, is going to be the elevation of B minus the elevation of C. So 24 minus 15, H3 is equal to 9. Now we can get our Q. Because we have a Manning's coefficient n, we're going to use the Manning's equation. HF is equal to 0.29 n squared LQ squared over d to the power of 16 over 3. And we already got the head losses of HF1 and HF3 earlier, which is 6 and 9. So we're just going to simply substitute it to our equation. So what we are going to find is the discharge flowing towards reservoir C. So this is what we're going to find. So this is what we're going to use. So HF3 is equal to 10.29 n squared LQ squared over d 16 to the power of 16 over 3. So 9 here is equal to input at all the values. So this is the properties of pipe C. And we have an answer that QC, or the discharge flowing towards reservoir C, is going to be 0.014 meter cube per second. So for our problem 3, same with problem number 2. But this time we are going to use the Hazen's formula, given C sub 1 is equal to 100, and we are going to compute the discharge flowing towards reservoir A. We used 9 meters to find Q for reservoir C, and now we're going to use the 6 meters for finding a reservoir A. Okay, now using the Hazen-Williams formula, we're going to compute for our discharge Q for pipe A or reservoir A. So we're just going to substitute the values to the given equation, and we can get Q. So direct substitution, head loss 6 and 1200 length, unknown Q, 100, the Hazen-Williams coefficient, and 0.30, the diameter. We're just going to convert it into meters, and we arrived to an answer of 0.0667 meter cube per second. That is our Q1. Now that's it for our topic and my discussion for this topic.